Thanks very much for hosting me. I'm very grateful for the opportunity. My name is Matt Culver. I'm coming from a company called INCAS, which is an innovation center for advanced sensors and sensor systems. So I'm going to be talking about sensor technology and the role of sensor technology in data. We produce a lot of types of sensors at INCAS. Everything ranging from all kinds of weather and soil sensors to help deaf people visualize sounds, to mathematical models of the human cochlea, some kind of psychophysical type of sensors as well. But I'm not going to talk about any of those. Oh, by the way, I remember you mentioned earlier about oil sensors. And we also produce, I added this slide a second ago, oil sensors that map underground oil reservoirs. I won't be talking about those either. Right? What I want to talk about is actually a kind of sensor called a cognitive sensor, which we're working on this team. But before I do that, I want to say something about data. Right? We're doing a lot about data. The topic of this talk is about data, and all of us are thinking about it, I suppose. But what is data really? I think that's an important question to ask before a talk like this. Is data in the world, as such, something that we can just harvest from objects and from things? I'd argue no, actually. Data is a construction. And before we look at what sensors do or what data is, we have to understand that data is an artifact of human technology, be it the technology of writing, the technology of counting, or more advanced technologies like, we'll say, electronic artifacts like sensors, like computers, and like other devices like that. But during this talk and during the future talks, let's not forget that data is a construction arising from design, so it doesn't reflect any fundamental reality. And there's often a misconception that data is the hard truth, right? And that's never true. And then I find that such an important point that I'd like to begin my talk that way, not just to frame research in cognitive sensors, but research in all sensors, right? Data is a construction. Let's look at a very simple sensor. This is a microphone, I guess you can't tell. It's a part of a microphone that we built. And let's look at how it works, right? Just as a starting point. Now, microphones, I have the world down there because I think it's also important that microphones don't exist in space. So they don't exist in some kind of weird hyper-reality. Microphones exist in the world. And so does the sonic signal. So let's say some kind of vibration in the air that is more or less equivalent to those kinds of vibrations which humans are able to hear, as it were. Okay? Well, when that vibration happens, a membrane on the sensor is activated. It vibrates a little bit. Those vibrations are translated into zeros and ones, and that's data. What does that mean, actually? Absolutely nothing. That data is absolutely meaningless, and there's so much of it. And that's when we talk about big data, we can think of fun things to do with it and so on. But don't forget that at its core, all data is meaningless. Those zeros and ones in another phase can be represented, of course, as waveforms. We all recognize that as sound. That's the kind of information, right? But the information for whom? Not for me or you, actually. It's information for acousticians. Well, maybe you're an acoustician, I don't know, right? Everybody besides acousticians, we don't know even what that means, right? So even though this is technical information, we can't forget that information is always for somebody or within a discipline, right? In other words, what data is and what information is, it's really a very narrow slice of human knowledge. Let's not get ahead of ourselves, right? Nonetheless, there's lots of it, so well, we better make the best of it. And it's not going anywhere soon. There's lots of fun stuff you can do with it. But I don't want to belabor the point or beat it to death, but it's a really serious question of who is this data for. After all, only some people can interpret it. It isn't for those who cannot, yet we produce it for them all the time. So let's look at that signal, actually. I said before it's uninterpretable to anybody but an acoustician, but even the best acoustician in the world could not tell me if that signal was sound or noise. Why? Well, what's the difference between sound and noise? Well, actually, that's a very complex question, to be honest, right? There is no sensor in the world that can do that every human child or every human being can do, distinguish sound from noise. Why is that? Well, that's because it's a psychological process, distinguishing sound from noise. There's no different signal for sound than there is for noise. Right? So when we think about big data and using big data, as it's called, what I'm interested in is giving meaning to that data. Right? Not only by virtue of my scientific analysis, where I sit and look at huge pools of data and think about how to give meaning to it, but also by virtue of the device from which that data arose. Right? So the data I've described right now has no reality in it. Those zeros and ones, yes, they correspond to fluctuations in the atmosphere that can be represented as sound in the human sensory organs. But I'm more interested in getting a data that has some reality beneath it, or that tells us something about reality. To do that, we need to invite human sciences into sensor technology, and in fact into all technology. Most technology anyways involves sensors of one kind or another. For some reason, technology is obsessed with sensors. Well, it's wonderful stuff. But it's, until now, almost completely devoid of the human side of things. And I find that very troubling, right? And in some ways, sensor technology has been around since we saw Galileo's telescope. That's great. That's a kind of sensor. But since then, until today, humans are totally barred. Human scientists are totally barred from entering the debate about technology. And where I'm working now, it's beginning to change, right? So it's a fun project. To give you a bit of an idea of who I'm talking about, this is the representation of the team who I work with. And I know that this could be maybe difficult to read a diagram, but we get a diverse team of people who have knowledge of sensors. That is let's say the natural scientists, so psychophysicists, acousticians, physicists, and others. And we also invite people who have knowledge of the senses. Those are usually human scientists. Now, let me backtrack to an earlier talk where we were told that the goal of science is has to do with the notion of control. That's actually indeed the goal of hard science. But that's not what we call maybe natural science, or knowledge of sensors. That's not the goal of the human sciences, right? No psychologist, no sociologist, no anthropologist seeks to develop their science to control anything, right? So we have a bit of a different goal between our two sides, but merging them together promises to add a lot to the kind of technology that we're seeking to develop. I'll come back to this makeup of the team in a minute. Let me first give some examples, right? Okay, so we talked already about how microphones face the world. Yeah, sorry to use such a weird term, but it works for in multidisciplinary teams. These are weird terms. We saw how microphones face the world. We can see also how humans face the world in a very different way than microphones do, right? Why? Well, humans in the world as sensors are always situated, right? They also involve all of their senses, right? Experience for humans is multimodal. So if we're going to build a kind of sensor that resembles in any way a human, that sensor has to take into account the multimodal nature of human interaction with reality. Also, more complicated still, knowledge, intention, information, desire that individuals have that maybe is not shared by others. So our perception of that sound is contingent on our knowledge. If there's any expert musicians in here, maybe you've recognized the music of a man known as one of the greatest visionaries of our time in terms of modern classical music. So nonetheless, the same signal to different people can be heard in different ways. The information is not in the signal. That is knowledge that's accumulated through the human lifetime, right? I'm making the problem much bigger, but this is really how it is. If I asked you to describe what you heard, I'd probably receive, I don't know, let's say we could sort the descriptions into certain types of descriptions. Maybe we would receive 10 or 20 different types of descriptions from experts and non-experts. But probably if we really get something like this, which is a very accurate description of the music from the perspective of an expert. This piece, by the way, that we just heard, Crossplay is called, is one of the most written about classical pieces in contemporary times. Okay. Nobody would probably write this unless you're an expert musician, right? Knowledge and our interaction with reality is highly contingent on our knowledge. That's the nature of the problem. The nature of the problem is essentially the human conceptualization of reality has nothing to do with the sensorial representation of reality, right? There is no connection. What we propose is a way to get around this problem, right? It's a way to build sensors that have psychological validity. This is a difficult process. Essentially, what we want to do in a nutshell, I'm very sad I only have 15 minutes, but maybe you could be happy, is that we want to model human cognitive processes and code them in artificial intelligence algorithms. And we'll still produce data, but that data will have some psychological validity because it will reflect human reality. Right? So such a sensor could, in theory, we're not building this sensor, but just to give an example of what it could do, could in theory, knowing the profile of the user, to determine if a certain sonic signal could be interpreted as sound or as music or as noise, for example, right? Maybe even the same person interprets the same signal in different ways at different times in their life, at different times in the day, after a few years, whatever, right? So this is a complicated issue, but let's look at a real application, right? I don't want to build a noise or music detecting sensor. It would be fun, but nobody would buy it. We're a private company, so we have to be looking for market possibilities too, right? Here's one of our colleagues who has a sensor city in Ljubljana, Slovenia. This is the Josef Stefan Institute. They're a nuclear institute there in Slovenia. And they have a bunch of sensors spread all over Ljubljana. And they can tell you all kinds of data about what you see of current, air temperature, even the brightness of the lights to which these sensors are attached. And you can see that plotted over time, over days, months, or even years. But what does it actually mean? Nothing, right? What does this mean? Really, it's just that it doesn't take anything volume field. So again, to extend the analogy one last time, a cognitive sensor will be different from the ones I just showed you, because it will be able to tell you if you as an individual belonging to a certain group or classification of users would likely be comfortable or, would probably better stay inside. Right? Okay. Now, this is not just some kind of fun game I'm proposing. Hey, let's imagine the funniest cognitive sensor you can think of. We're building one right now. The one we're building is called the habitat sensor system. The idea of the habitat sensor system is to predict human behavior in a certain place based on the urban morphology, the things in that space, let's say, as well as the sounds in that space. We believe that these things are correlated. The idea is, of course, again, not an academic exercise. We actually propose building a tool that could be used by police, a tool that could be used by the municipality. They're doing suburban planning right now. And maybe a tool that could be used by the public themselves to look at how their neighborhood and so forth, to kind of encourage kinds of behaviors they would like to see in their living environment. So we have to find these correspondences, right, between human activities, the urban morphology, and the sounds of the place. Okay. Now you can see why the diversity of experts on the team is essential. The first step, of course, is to be able to characterize the sounds there as they are in the world. And we need microphones to do that. So we make reference to our statisticians and our physicists to build us some artificial sensors, which they've done. We've now installed about 200 sensors that record data 24/7 throughout the city of Assen, which is the capital of Drenthe province in the Netherlands. These are not all active right now, about 4 beginning, we're in the first phase, but they're all installed. So there's going to be in the end 200 sensors, and that produces a lot of data. Now we're on to the topic of big data. This is just one city. Okay. The numbers I'm about to give you probably won't shock you guys because you're used to seeing even bigger data, but nonetheless, we're talking about 600 terabytes a year, roughly 3 libraries of Congress. I think that's a very American analogy. Nonetheless, it's a lot, but not tons. It doesn't matter. It's still too much to actually study by yourself, to make sense of, to give meaning to, which is the fundamental problem. Now we need to give meaning to data. So how do we do that? For that, we need to use people on the other side, people with knowledge of human senses. We make reference to our psychologists, anthropologists, sociologists, and linguists. Anthropologists describe human activity using standard anthropological and ethnographical methodologies throughout the city of Assen. They've been doing this now for over a year, and they produce field notes, which are digitized. There's trouble, though. The conceptualization of reality held by the anthropologist might be different from the conceptualization of reality held by the user of that space. This is very obvious. It's very obvious, but even very simple with the games you can play. You ask people to draw maps of their environments. People who get around in the car draw maps like this. You can just see, you can already guess, hey, this guy doesn't walk around very much. People who take the train, they even draw the train on there. That's how fundamental the train is to their connection to Assen. And it's not a joke, you can really see people who commute to work on the train, that everything is in relation to the train station. Although the train station is not geographically central in the city. And people who walk or bicycle, which is often the case in the Netherlands, have a much more conceptual and interesting ideas of the city. These realities are distinct though, right? So if we're going to build a sensor system that reflects human knowledge, we have to be able to account for different kinds of knowledge and awareness. Right? What we do is like to layer all of those different kinds of cognitive maps. Using a program called SketchMapio together with the University of Munster. Too bad I can't talk about that. It's really fun topic. But look at behavior, right? Behavior is another issue that the anthropologists document. This reminds me of some of the other talks earlier. We look at posture, speech, gaze, gesture, and a number of other factors described in the field in real time. Right? I don't propose putting sensors on these people. But why not? Because human activity is very complicated. Right? The other thing we need to define are places. The components of those places, which we call affordances, in accordance with the philosophy of psychological ecology, ecological psychology. And so affordances are objects that facilitate action, that give borders or plain spaces to areas and allow or facilitate certain kinds of human behavior. These have to be correlated. The reason we want people in the field and not just to put a sensor on their body and do it this way It's because human activity is too difficult to predict anyway, even with a sensor on them. So looking at this map here, if I asked you what kind of activity you would expect, or anyway, if I asked myself what kind of activity I would expect besides driving, I would say probably nothing. But actually, when the field workers went here, they found a rather lively, it doesn't look so lively, but nonetheless, it's called a rather lively environment where people are regularly here hanging out. Because teenagers come here and they smoke cigarettes, they gossip, who knows what else they're doing. But they've repurposed this environment to suit their own needs. Field workers, essentially. The next bit, so okay, you can imagine we've gotten some sensors out there, we've made some descriptions of human activity, now we've got to tie it together. These things by themselves aren't really meaningful. What we do in the next phase is we use those physicists and acousticians, we combine them with some psychologists and AI folks. We attempt to describe the sonic environment. Right? Our first attempts were pretty effective, but impossible to really use. Somebody was annotating and trying to do an automatic classification of incoming acoustic signals, but this is too hard to do in real time, right? And also, the things that you hear or the things that you perceive might not be perceived by others. We don't want to presuppose any kind of ground truth here. That was the point of the psychological earlier. And what they try to do then is link certain soundscapes to certain urban environments by making what we call an acoustic fingerprint, or an acoustic signature, a representative sonic signal that comes from that sort of place, right? There's really interesting ways to calculate this, but we use basically a histogram and a bibliogram, which is a mathematical model of the human ear. Maybe some other time talk about it. Recordings are processed to result in a single representation, which is a histogram of energy values for a certain frequency or frequency bandwidth. Okay. Then we have this very interesting but complicated way to show how the representations are processed itself. And essentially, in a nutshell, what we want to do is link the sonic environment to the activities, right? Take out the urban environment. Basically, what we're saying is that with sound alone, we want to be able to predict what people are likely to be doing at a certain place, at a certain time, in a certain area. So, in the final phase, I'm wrapping up now, once we've established what sounds go with what places, we can model the psychological validity of those places, right? So when I say, hey, well, a park is a place, that's common sense, of course, but does it have any psychological reality? And if I say, well, running is an activity separate from jogging, okay, it's nice that I say that. We all might agree or disagree with that. But we want to establish first and foremost the psychological validity of those categories. We can make reference to the categorization. We modeled that actually by doing all kinds of cognitive testing, free sorting tasks, similarity matrices, and prototype analysis. Then we can model those in a multidimensional scaling or some kind of phylogenetic tree analysis. These in turn, I shouldn't be there, sorry. These in turn are modeled by our AI expert, right, who takes those analyses and formulates from them algorithm to reflect these cognitive tendencies among different groups, different users. Essentially, this algorithm can then learn to create a classifier to assign some sort of activity label, which has been previously established in the psychological tests, to label a given audio file for a certain activity. The result is a layer on our maps. This is what we envision. A layer on top of our standard maps of the world that shows where likely activity is is probable to occur. So to be clear, it's not a video camera. We're not saying what's happening where. We're saying for this kind of person at this time of day, this is likely to be happening, or this could happen here with certain possibility. Right? So what I've just described then is a lot of data coming from, for example, sonic environment. I didn't have a chance to talk about social media, but people are checking in all the time and tweeting about all kinds of stuff. You can mine that data, as well as data from weather stations and all kinds of other sensors we have at our disposal. We want to combine that also with more data. Well, great, you might say, wonderful, we just introduced more data to us. We want to combine it with psychological data coming from human categorization tasks that reflects some sort of psychological reality underlying perception of these events. Thus, organizing and giving psychological validity to the data itself. Right? Changing data to knowledge through humans is the goal. So aside from giving meaning to data and what we call cognition sensors, or let's say modeling human cognition for artificial sensors, we also believe this promotes knowledge exchange. Right? So we have other projects that I'll talk about them in a second, or I'll list them anyway, that takes the domain of knowledge, research, and sensor technology out of the hands of the scientists and gives it to the experts in the population. After all, who knows more about somebody's environment than the person who lives there, right? Who knows more about, for example, fishing places than the fishermen, right? This is the kind of stuff we want to model. This is what we want to respect and give adherence to. And we also talk a lot about tacit knowledge and know-how, right? So I'm not interested so much in what you know propositionally, that Amsterdam is the capital of the Netherlands, but what you know tacitly or through know-how. Okay, so applications right now being explored. We're launching this pilot project right now in Aachen, as I just described it. On Sunday, I'm going to Vantaa, Finland. They're also doing some redesign. We met people operating on the project there. Environmental monitoring is in development. Now, the assisted living communities are a really interesting case. There you have nurses who are able to diagnose patients at their institution effortlessly, right? They hear a cough, they hear a sound. They're like they're expert systems, right? However, they're quite old. They have no PhDs, they have no advanced learning, they're just professionals. They do their job very well. We proposed a methodology based on the one I just described to be able to diagnose, classify coughs, and other human sounds artificially, but in a way that's modeled on the human cognition as held by these experts. Also panic detection is another one they're using mostly. Okay, that's it in a nutshell. I hope I didn't go over too much. I'm happy to hear questions. Thanks very much for hosting me. I'm very grateful for the opportunity. My name is Matt Culver. I'm coming from a company called INCAS, which is an innovation center for advanced sensors and sensor systems. So I'm going to be talking about sensor technology and the role of sensor technology in data. We produce a lot of types of sensors at INCAS. Everything ranging from all kinds of weather and soil sensors, sensors to help deaf people visualize sounds, to mathematical models of the human cochlea, some kind of psychophysical type of sensors as well. But I'm not going to talk about any of those. Oh, by the way, I remember you mentioned earlier about oil sensors. And we also produce, I added this slide a second ago, oil sensors that to those kinds of vibrations which humans are able to hear, as it were. Okay? Well, when that vibration happens, a membrane on the sensor is activated. It vibrates a little bit. Those vibrations are translated into zeros and ones, and that's data. What does that mean, actually? Absolutely nothing. That data is absolutely meaningless, and there's so much of it. And that's when we talk about big data, we can think of fun things to do with it and so on. But don't forget that at its core, all data is meaningless. Those zeros and ones in another phase can be represented, of course, as waveforms. We all recognize that as sound. That's the kind of information, right? But the information for whom? Not for me or you, actually. It's information for acousticians. Well, maybe you're an acoustician, I don't know, right? Everybody besides acousticians, we don't know even what that means, right? So even though this is technical information, we can't forget that information is always for some. During the future talks, let's not forget that data is a construction arising from a design, so it doesn't reflect any fundamental reality. And there's often a misconception that data is the hard truth, right? And that's never true. And then I find that such an important point that I'd like to begin my talk that way, not just to frame research in cognitive sensors, but research in all sensors, right? Data is a construction. Let's look at a very simple sensor. This is a microphone, I guess you can't tell. It's a part of a microphone that we built. And let's look at how it works, right? Just as a starting point. Now, microphones, I have the world down there because I think it's also important that microphones don't exist in space. So they don't exist as some kind of weird hyper-reality. Microphones exist in the world. And so does the sonic signal. So let's say some kind of vibration in the air that is more or less equivalent or within a discipline, right? In other words, what data is and what information is, it's really a very narrow slice of human knowledge. Let's not get ahead of ourselves, right? Nonetheless, there's lots of it. So, well, we better make the best of it. And it's not going anywhere soon. There's lots of fun stuff you can do with it. But I don't want to belabor the point or beat it to death. But it's a really serious question of who is this data for. After all, only some people can interpret it. It isn't for those who cannot. Yet we produce it for them all the time. So let's look at that signal, actually. I said before it's uninterpretable to anybody but an acoustician. But even the best acoustician in the world could not tell me if that signal was sound or noise. Why? Well, what's the difference between sound and noise? Well, actually, that's a very complex question, to be honest, right? There is no sensor in the world that can do that every human child or every human app underground oil reservoirs. I won't be talking about those either. Right? What I want to talk about is actually a kind of sensor called the cognitive sensor, which we're working on this team. But before I do that, I want to say something about data. Right? We're doing a lot about data. The topic of this talk is about data, and all of us are thinking about that, I suppose. But what is data really? I think that's an important question to ask before a talk like this. Is data in the world, as such, something that we can just harvest from objects and from things? I'd argue no, actually. Data is a construction. And before we look at what sensors do or what data is, we have to understand that data is an artifact of human technology, be it the technology of writing, the technology of counting, or more advanced technologies like, let's say, electronic artifacts like sensors, like computers, and like other devices like that. But during this talk, and